Hello guys, welcome back to another exciting video. So this video marks the beginning of a new series I plan to introduce, which is basically understanding Transformer LLMs from the bottom up, right? So if you've been following along with my channel, we have been working with different multi-agent application, LLM applications and stuff like that. We have done vastly a lot of projects on it. So one of the things that I see most of us skipping, including me at the initial stages, is we skip the LLM understanding of the LLM and jump straight into its applications and doing really cool projects. But at some point, you'd have to come back and understand things at a fundamental level. You'd have to be able to understand your multi-agent systems, your agentic systems, your LLM applications in a better way, right? So this is what this series is for, understanding LLMs from the bottom up, so that in case you have any errors or your LLM is behaving in a way that you don't expect it, then you can know how to go about solving that problem or addressing that problem, right? Also, it helps us to also become innovative. If you want to maybe build upon what has already been developed or built on, then you can go ahead and build up on that using the knowledge from this that you learn from these videos, okay, from this series of videos. So basically in this video we'll be focusing on understanding the LLMs from the ground up. This is the first video, and we're going to be focusing on working with tokenization or tokenizers in this video. And tokenizers are one of the components of a transformer LLM. So if you know what the transformer LLM is, just ignore the transformer part. Think of it as LLM, which is large language model or large language models, LLMs, right? So let's go ahead and jump into it. So this is going to be a crash course introducing you to the first fundamental concepts, components of a transformer LLM or just an LLM, which is a tokenizer. So this is going to be a crash course, but it's going to give you all the fundamentals information that you need in order to work with LLMs and tokenizers specifically. Okay, so we're going to be covering introduction to LLMs for those of us who are new. We're going to go ahead and talk about LLM. By the way, if I say LLMs, I mean large language models. So we're going to cover introduction to large language models. We're going to look at the different components of the large language models, specifically focusing on the transformer LLMs. We're going to be looking at what a tokenizer is, and then we'll look at we do a code implementation of how to tokenize text using GPT tokenizer, GPT-4 tokenizer, the StarCoder tokenizer, and the Galactica tokenizer. Okay, and then we'll look at the different tokenization methods. We'll look at one of the most famous, which is the Byte pair encoding method, and then we'll visualize how GPT-4 encoder tokenizer encodes information within text. Okay, and then look at the different factors affecting how the different tokenizers behave, and then we'll have some little add-on knowledge to it, and then that has to be the end of the of this video. Okay, so let's jump into the first part, which is basically understanding an LLM. So as I said earlier on, an LLM stands for a large language model, right? So if you go something like ChatGPT, if you go to ChatGPT and you type in something, it outputs information back to you, right? That it at the back of it is using a program called an LLM, a large language model, which can understand human text and respond back to us in human text as well. So that is basically that's basically the technology behind, or the machine learning models behind ChatGPT. These are called large language models, and not only ChatGPT, any LLM, any basically chatbot system out there, most of them use large language models these days. So the technology behind them, or the machine learning models behind them, are called large language models. Okay, so where did this whole concept of large language models came from? So in these days, everywhere you go, you hear probably a word AI, LLMs, large language models. These have become buzzwords. So how did all this begin? So let's take a big time travel back in time to 2017. So in 2017, this new research paper came out called Attention is All You Need. And in this Attention is All You Need paper, which you can read from scanning this QR code, they introduced the concept of transformers. So transformers help to deal with NLP tasks, right? So they can also do other set of things. But transformers was initially used for machine translation. But later on, as developers work with it, as researchers work with it, they found out that, hey, we can use transformers way beyond just doing machine translation. So they started using transformers for various activities, such as the chatbots, ChatGPT, Gemini, image generation, speech synthesis, video generation, and all other hosts of stuff. right? So all this thing came from the fundamental and the great research that was done in 2017 in a paper called Attention is All You Need. And you can read this paper by scanning this QR code. I don't want to go much into it. If you're really curious and want to find about what's really in this paper, and if you've been in the AI space, I think you probably came across this thing of Attention is All You Need, which is this research paper. And I really encourage you to just look at it, read through it. You don't have to understand every tiny bit of it, but just read through it and try to grasp a bit of it. So you can use this QR code right here. It's not a compulsory, but it's good to do. Okay, so let me just so we have this. I'm just going to give you a simple idea of how LLMs work, right? So let's say you go into ChatGPT and you type in something, right? You say maybe hello world, and then you press enter. So that gets sent to so you can think of it as our Transformer LLM. I call it Transformer, but you can think of it as our LLM, right? So it goes to our Transformer LLM, and our Transformer LLM. So we have this text right here. That's one small step for man, one giant leap. I hope you most of us know this phrase, right, from Neil Armstrong when they went to the moon. So that's one. The whole phrase is that's one small step for man and one giant leap for mankind. So we have these two gaps left. So we have for and mankind. So we expect our Transformer LLM to be able to fill in these gaps that we left. Okay, so we've set this information. It goes into our Transformer LLM. Our Transformer LLM predicts the next likely word. So it predicts this next likely word by considering all the previous word that came before it, right? So that's how it works, right? And then this newly generated text along with all the previous ones, so that's one small step for man, one giant leap for, that goes in as our new input to the LLM. And the LLM predicts the next word by taking all the previous words into account, right? So how does LLM predict the next word? This is information that it learns from training. So LLMs are trained on vast amounts of data. So basically the whole internet is used to train an LLM. So it has a good understanding of human text and how to predict the next word. And if you've been on the internet, this phrase of that's one small step for a man, one giant leap for mankind is all over there, right? So the LLM probably came across this, so it can predict the next word. So you might be thinking, okay, then LLMs are basically memorizing stuff. Not really. Some people call them statistical parrots. Yeah, so they basically do this kind of predicting using some statistics and memorize information that they learned. I wouldn't say really memorized, but yeah, that's basically it. So they use some statistical and mathematical stuff to predict the next word based on information that they have learned from training as well, right? So they predict the next word and then on it goes. That's the same reason when you go into ChatGPT, you see your text being streamed back to you, right? So if you go into ChatGPT right now, you type complete this sentence. That's one small step for a man, one giant leap for. It should be able to complete this sentence, right? Yeah, so you can go ahead and actually try this out in your own. Okay, now that you have covered that, let's go ahead and look at the different components of a Transformer LLM. But before we do that, let me go ahead and let's try to actually do this ourselves so that you can see how this works in real life. Okay, so I'm going to go into my browser and I'm going to go ahead and open ChatGPT. Okay, so I have my ChatGPT loaded up here and I'm going to say, please only say that's one small step for a man, one giant leap, and then dash. Let's see what we get back. So I assume that it should predict this correctly, but let's see what we get back. Okay, this is taking a bit of time. Okay, something went wrong. Let's try again. Okay, for mankind, right? So it predicted this properly, and it said that this was from Neil Armstrong when they went to the moon in 1969. So that was predicted correctly, right? So this is the process behind it, and you can see how we get text being streamed back to us, right? Because when it generates this word for, it outputs it, and then the outputted word plus all the previous word go back in as input, and then the next word is predicted. and then the result of that goes back in, and then the next word is predicted. And that's why if you're working with a chatbot, you can see the stream text, right? It doesn't come as one chunk of text, it comes as streamed, so you can see for mankind. Perfect. So that's basically how these LLMs work on a surface level. So let's look at the different components of a Transformer LLM. So if you have ever come across Transformer LLMs, you know that they're more complicated than this, right? But this is just a short, simplified version for you to understand. I don't want to display the whole diagram to scare you guys off. This is just a short diagram for you guys to understand. When I was learning this, I go into some videos or some articles and I see people having this complicated view. I'm like, what the hell is this? Right? I don't want you guys to have that experience, so I have made this simplified diagram to make it easier for you. So we have our input text right here. That's one small step for man, one giant 4, and then it goes into our LLM, which has a tokenizer and a bunch of transformers. That's why we call it a Transformer LLM. And mostly this series will focus on understanding what really goes on in these transformers, because that's the juice of it. That's the main thing. And then you have the LLM head, which is a bunch of neural networks. And then finally you get the predicted word, right? So these are called stack of transformer blocks. That's basically what they are. Okay, so don't worry so much about this diagram. Just know that we have for our Transformer LLM, which is this area right here, we have the tokenizer, we have the transformer blocks, and then you have the LLM head, which does the final prediction of the next word. Okay, so what is a tokenizer? So we'll start from the very first step, understanding this whole block right here. So the first thing is here a tokenizer. So what is this tokenizer? And that's what this video is going to be tackling, helping us to understand what this tokenizer is. Right, so you can think of a tokenizer as a section of the Transformer LLM that breaks down input text into subwords that we call tokens. Right, so this in the real world, these are not actually subwords some of the time, but just for the sake of simplicity, think of it as subwords. Okay, so we put in our text, that's one small step for a man, that's one giant leap for, that gets broken down into subwords. We call these subwords tokens. That's what the tokenization does. But computers don't understand text, right? So this text has to be converted into some kind of numeric representation. And that's where in the tokenizer, it's trained on a vast amount of data. So it's trained on so much data that it has basically it knows all possible words in a language, but not all of them sometimes, because words language is always changing and new words come into it, or sometimes the word that you're using is simply not in the training text, right? So the tokenizer has something called a tokenizer, a token ID, and then the associated token, which is just a word. So for example, hello is a token ID 1, and it's mapping to the word hello, right? And then it goes on and on. You can think of this as for all English words, right? All the amount of words that tokenizer was trained on. Amount of words, I mean the amount of unique words the tokenizer was trained on, and that is called the tokenizer's vocabulary size. Is the number of words that it was trained on. A tokenizer has a table, which is this table right here, called the tokenizer's vocabulary. The tokenizer model has a vector representation of each token in its vocabulary. Each of these vectors is called a token embedding, right? So the model's vocabulary is just a set of all the unique words that the model was trained upon, and it has an ID mapping to all these unique words, as you can see in here. Okay, so that's basically a general overview. So we take in some inputs and then we break down into subwords and then get the associated IDs of the subwords, right? And as I said, they're not always like full meaning English words, and we'll say this in a second. It might be confusing at the moment, but please bear with me. We'll actually implement the code of this and we'll see how this works just in a second. So the first tokenizer that we'll look at is a GPT-2 tokenizer, and this was developed, I think, back in 2019, if I'm not mistaken. Yeah, so we're going to be using the GPT tokenizer to try to understand how tokenization work in actual practical sense. Really, I don't want so much focus on the theory, because I believe that we humans understand things more through hands-on experience, right? So instead of just bombarding with a lot of theory, let's actually get into the code so that you can see it for yourself and develop your own unique intuition about what a tokenizer is, right? Okay, let's get into it. So I'm gonna go back in here. So you can just go to Google and then search for Google Colab, right? Once you search for Google Colab, make sure it will bring you to a page like this, or click on it. It will bring you to a page like it will bring you to a welcome page. Go in here and simply say open a new notebook in Drive, and then that would open a new open for you this kind of notebook, right? Perfect. Okay, so once we have that notebook open, you also probably have something like this. Once it's open, for me I just close it because I don't want the AI thing. So it's just a Gemini AI to help us edit the text, all right, edit our code. Okay, so once you also need a Hugging
once
Face,
you're in here,
you can just click on access token and then go ahead and generate an access token, right? So for me, I'm going to go simply copy one of my access tokens that I have from a previous project, and I'm going to go in here. I'm going to click on this key, basically stands for secret keys. Go in here, say add a new secret, and then say hf underscore token. Make sure it's all caps and it's exactly this format, hf underscore token, and then you copy and paste in the Hugging Face token that you generated from your page. So click on access token and then generate an access token. I don't want to reveal my access tokens because I already have some access tokens, but it's barely straightforward. Just click on access tokens and then go ahead and generate one. So I'm going to go ahead and simply copy one of my access tokens, and I'm going to go ahead and paste it in here. Before I do that, let me rename this to be let's say LLMs, and then let me say this is going to be tutorials. Today is a bad typing day for me, yeah, but anyway, so let me go ahead and get my access token and then simply paste it in here, and I'll be back recording. Okay, so I'm going to paste in here my access token and then simply press enter. Okay, so just come in here and then make sure I click on this button so that it can be accessed by my code right here. And this is how you can read the access token, but since you're using this as an environment variable, our code should automatically pick it up. So you can close this for the meantime, and then we can jump into in here. So you need to go into connections right here and then say change runtime, and then make sure it selects a T4 GPU. So we need a GPU to play with this tokenizer, so make sure that you have a GPU T4 GPU running as selected as your runtime environment. Once that's done, we can go ahead and actually begin to code. So we're going to go ahead and import a couple of things right here. So these are libraries that you're going to be using by default installed within your Google Colab environment, so you don't have to do anything. So all you have to do is just go ahead and we can create here and say the first thing we're going to go ahead and just say let me rename this a bit to be called let me say imports right here. I'm going to say from Transformers, we're going to go ahead and import auto model for casual LLM, and you're going to also import auto tokenizer. So run that, and that's going to import those two things. We actually don't need this for the moment, but just leave it in there. It doesn't really matter, but we're mostly going to focus on using this right here. Okay, so once that we have this done, the first we also need to go ahead and specify our tokenizer name. So tokenizer underscore name, and this is going to be using a tokenizer name, and this tokenizer name is called open AI hyphen community, and then hyphen /GPT GPT-2. So we're going to be using the GPT-2 tokenizer. So pronouncing this word sometimes can be tricky, so that library is importing, and you're using the GPT-4 the T4 GPU. So when you say tokenizer, the tokenizer is going to be equals to, we're going to say auto tokenizer dot from pre-trained model, and then we pass in our model name right here, which is OpenAI hyphen community /GPT-2, and we run that. That's going to go ahead and download the model, and once it's done downloading, we can go ahead and now use this model. So let's go ahead and have a sentence right here. So let me just go ahead and bring in a sentence that you're going to be using. So I'm going to create another code cell. I'm going to go ahead and copy a sentence from one of my pages and then simply bring it in here. So I'm going to paste in the sentence that I want to bring, and this is just a sentence right here. It's just a Python docstring saying hello world, blah blah blah. Sorry, not a docstring, but yeah, pre-coded string, right? So we're going to go ahead and get the token underscore IDs, and and this is going to be equals, so we're going to say tokenizer, and then we pass tokenizer, right? And then we pass in our sentence right here. Sentence, pass in our sentence, and then we close off that and we say dot input hyphen IDs, just like that. And if we run this, it's going to return to us all the different IDs of these tokens. Let me just keep them here and then rerun this cell again. So we run this cell, you can just press this button or shift and enter on your keyboard. So you can see this set of all these unique IDs that we get back. So each ID has, like, you can see some of them are double because some words have been repeated. So yeah, that's basically the token ID. And where does this really come from and what does this mean? Remember this diagram, right? So that's where we're getting these IDs from our tokenizer. Okay, so I'm going to minimize this for now. And to make this even more better to understand, I'm going to have a way of visualizing this information. So I'm going to go ahead and simply drop in a code block right here. So I'm going to paste in that code right here. So this, what it simply does is that it adds colors to different tokens and stuff like that. So if I run this cell, we should now see everything formatted in an easier way to understand. So if I scroll down here, you can see this is how the tokenizer has chunked up our input, which is this whole Python string, into individual tokens, right? So these individual tokens can then be sent into the transfer. There's some other steps involved, but you can think of it as being sent to the AI LLM model, and it's going to process it and then generate outputs based off of it, right? But this is what goes in. You can think of it like that, but there's another step, which is embedding step. We'll look at that later on. But this can be thought of as how the LLM understands our input text and how it chunks them up. So you can see LLM is one word, but GPT-2 tokenizer says LLM is one token and then M is another token. October is treated as one token. Current is treated as one token. You can see we have this Python code right here. Each of these is treated as kind of a different tokens, right? So if you're running a program, you can see this is 840 and 847. This is treated as one single token, and this is treated as two different tokens. So if you're using this tokenizer to do some math work, then you can see how it can fail, because it's treating 847 and 840 as two different things, which is not true, right? They're all numbers. Yeah, but basically you can see how LLM chunks things up into sub tokens, right? So that's basically it. So let's look at some of the characteristics of the GPT-2 tokenizer. So the tokenization method it uses is a BPE, which is a byte pair encoding tokenization method. It has a vocabulary size of about 50,000 words, right? It also has a special characters such as which indicate positional information within the text, such as end of text and other stuff like that. So that's the GPT tokenizer from the year 2019, and you can see how it tokenizes stuff, right? Not perfect, but quite good, right? So you can see transformer is transform, and then ERD is treated as separate words. Okay, so once we have that done, let's go ahead and continue. So I want to create a function that I can use so that we can test all these other methods. So I want to basically pass in the tokenizer name, and then all this get done without me having to manually type out that code. So we're going to create a function right here. So we're going to say dev, we're going to call it test underscore tokenizer. It's going to help us test our tokenizer. We're going to tokenizer name, the name of the tokenizer. We're going to take in the sentence. You're going to take in the color list, and what you're going to do is this right here. We're going to pass in the tokenizer underscore name right there, and then you're going to go ahead and say token underscore IDs, and this is going to be equals to the following. So I'm going to say tokenizer, so the dot passing the sentence, call it passing the sentence, and then getting the IDs from it, and you're going to go ahead and do the coloration thing which we did previously. So I'm going to go ahead, let me just grab this for loop here, and then replace this with the for loop, paste that over there, and then indent that. Okay, perfect. So that's all you need to do. So this is going to be passing a tokenizer. It's going to do for all the things, and then all the colorization and all that sort of stuff. Okay, perfect. So once you've done the GPT tokenizer, let's look at the other tokenizer I wanted us to experiment, which is the GPT-4 tokenizer. So let's look into it. So the GPT-4 tokenizer, now that you have this function, it's much easier to do. All you have to do is simply say test tokenizer, and then you're passing a tokenizer name. So you're going to be using the GPT-4 tokenizer, and it comes from this repository on Hugging Face, and I'll share with you the link to this just in a second. But basically this is, so it says send over and then / GPT-2, passing our sentence and our color list, and then we get back. So it's going to go ahead and load the tokenizer and then do the fuzz encoding. So you can see GPT-4 has a better representation of tokens. So you can see this 840 and 847 are all treated as single individual numbers, and in here it was not treating them as individual numbers. So GPT-4 is probably good at math than GPT-2 because it kind of represents information more accurately than GPT-2. Also, you can see if it comes to our program, right? So that's why some models are better at coding than other models. So you can see all this tab in Python is being treated as one token, and in GPT-2 it's treated as different tokens. So GPT-4 is probably good at representing Python code than GPT-2. So hence it can generate and interpret code better, right? And that you can test these different tokenizers, and this really affects how they understand text and how they can process information. So you can see Transformer is represented as one token and all that, right? So some models are better than in mathematics than others, and others are better in coding than others, right? So due to this way of representing information. So we'll look at another tokenizer. Let's look at some of the characteristics of the GPT-4 tokenizer. So it uses the byte pair encoding method. Has a vocabulary size of 10,000 words or 10,000 tokens, and can also say white. It also supports white space and coding support. That's why you can see this is one single tab in Python represented as one single token, while GPT-2 represents as three different tokens, right? So this can do better at coding, right, because it supports better white code support, which is good for coding, right? So these different tokenizers have their pros and cons, right? Okay, now let's look at another tokenizer, which is the star encoder tokenizer. So I'm going to create another coding block. And to use this, I'm just going to go ahead and simply copy this file and then paste this line, right, and paste it in here. So we're going to go ahead and change the tokenizer's name. So we're going to get it from this library called, this repository called big code, and then the the tokenizer name is StarCoder 2 -15 billion, the 15 billion parameter model. Okay, I think this is 15 billion parameter model. So that's the model that you're going to be using. Okay, so one thing I also want to confirm is if you want to read about the GPT-4 tokenizer, you can scan this QR code. It takes you to the the Hugging Face repository for this tokenizer, and you can read more about it, right? So each tokenizer has repositories for it, and also the StarCoder 2 and the Galactica tokenizers, which you're going to experiment with just in a moment. You can read more about them using these QR links right here. Okay, so for now I'm going to go back in here. You're going to be using this tokenizer. Okay, so to use this, I'm just going to go ahead and simply execute this cell right here, and you're going to go ahead and download the tokenizer and then generate the different basically tokens for it, token representations. So you can see one of the good advantage of the star encoder is that it encodes the tab as one single token, represent the tab as one single token, and also it's also going to be good at math better than GPT-4 tokenizer, because each individual number is represented as an individual token. So I think this model will be better at this tokenizer will be better at understanding mathematical concepts than the GPT-4 tokenizer, right? So you can see it right here, and you can actually try the other tokenizer that we have, which is the Galactica tokenizer from Facebook. It was developed in I think I forgot which year was that, but yeah, let's test it out and let's see. Let me just delete this, copy all that, and then go in here and simply paste it in here. So paste it in here, and then you're going to go ahead. It's going to be from Facebook. So Facebook, this is the account on Hugging Face, and you're going to say Galactica, and you're going to use the 1.3 billion parameter model. So I'm going to say Galactica /1.3 B model. That's it. And if you run this, let's see what we get back. So if you run this, we're going to go ahead and download this model, and then simply run it. So you can see it also is probably good at mathematics, because it does it's good at mathematics because each number is represented as individual tokens. And you can see this one here was representing a space and a plus symbol as one single token, but the Galactica was representing that as a single, the addition sign as a single token, and spaces as individual tokens. And for tabs, it was using one token. So it's good at coding and mathematics. So you can see how the different tokenizers represent information and what are the advantages of each of those tokenizers. Again, you can read more about these tokenizers using by scanning these QR codes on the screen. So let's look at the tokenization, the different tokenization methods. So one of the common ones is the character tokenization. This is probably the simplest to understand. What it simply does is that given a word or given an input sequence, it simply breaks it down on character level. So you can see hello as a word has been broken down into HELLO, each as a token. So each letter will be represented as a token. So you can see in here we have H being represented as a token, just for an example. Okay, so that's a character level tokenization. And then we have word level. So word level, it explains itself. Given a sequence of inputs, it breaks it down into words, and each word will be a standalone token on its own. For example, here current is October, right? Transformers, prints, code width, all this, right? So all this is simply standalone words: main, name, if, standalone, right? That is word tokenization. And then we have what we call subword tokenization. So subword tokenization breaks down into words, and then sometimes separate separates words and characters. So you can see if you're given the input transformers, it can be broken down into, if you look at the GPT-2 tokenizer, it breaks into transformer as single token, and then ERS as another set of tokens. So that's basically a subword tokenization. And all the tokenizers you have looked at so far, all of them have utilized subword tokenization. So why subword tokenization? Most tokenizers today use the subword tokenization method. Why this? Because it acts as a middle ground between for the word tokenizer and the character tokenizer, blends the two into one, right? And it has a lot of advantages, such as it helps models to learn new words that they have not seen before, right, by utilizing other words that they have seen before in their training set. So for example, let's say a model has seen the word in this case here transformer before. So transformer is encoded as one token, but it has not seen transformers before, so the ERD gets as a standalone, right? Yeah, so that's basically the advantage of using subword tokenization. Blends the two of the blends the best of the two worlds. So good. So one of the common different tokenization methods using in the subword tokenization is the use of byte pair encoding, word piece tokenization, and unigram language model, right, which is used by the T5 tokenizer. We also have word piece, which is used by the BERt tokenizer, and you have the byte pair encoding, which you have seen used by the GPT tokenizer, GPT-2, GPT-3, the star encoders that you have looked at, and also the Galactica. They all use the byte pair encoding, and it's the most popular one used by most language models these days for tokenization. Okay, so what is this, and why we have seen why subword is the best, but what is this byte pair encoding really is all about? So to understand this, I have an example right here. For me, again, I think practicality is better than just a theory, so we'll go with that approach, and we want to see this how it works. So giving the training corpus of lower, lower, lowest, right? So what the first step we're going to do is initialize our vocabulary. Vocabulary are all the unique words in which a model was trained on, or all the unique set of words from a corpus. Corpus is a training data set. So, but in this case, you're going to think of it letters as words. So all the unique letters within our corpus. That's basically, so we have all of them right there. We include space as well. So if there is space, if there is tab, we include this as well. And then from the corpus, we begin to go ahead. So this is how our corpus looks like, right? We count the space as well. So we begin to work with step one, which is merge the most frequent pairs. So this, how do you know the most frequent pairs? And these are a set of rules that are called merge rules. So the rules that the LLM follows in order to, the tokenizer follows in order to merge characters together to form words in the byte pair encoding. methodology. So basically, the most frequent one is L followed by an E. So you can see L followed by E, 1, 2, and 3. So that's the highest frequency. So we are going to merge L and O. So we have now this as we add L and O to our vocabulary. So we merge this as 1, and then this as 1, this as 1, the other ones remains as the same. We go to step 2, merge the next frequent pair, which is now LOE. So LOE occurs, so we merge LOE, LOE. So we merge them, and then we add we add LO, so I skipped step 2. So we add LO to our vocabulary, which is the most frequent one. Then we go here, the next one is going to be LOE. So we also add LOE to our vocabulary, and then in our corpus, we merge all LOEs into one token. And then we repeat this for n amount of times following different merge rules, right? So at the end of the day, we have this whole vocabulary. So we can represent words like low, lowy, lower, lowest, lowest, right? So you can represent all this as individual tokens. And that is how you can see these things are being generated, right? Yeah, it takes a bit to understand, but just take a piece of pen and a paper and just write it down. When I was studying this initially, I had to simply write it down. So at the end of the day, using the byte pair encoding method, our model can understand subwords like low, lower, lowest, etc. Right. So to understand this even more, right, the best way to do it is to understand this even better through code. So I'm going to go ahead and you're going to learn how to visualize how the GPT-4 tokenizer uses the byte pair encoding to encode stuff. So the first thing you're going to go ahead and do, you're going to go ahead and install one of these libraries, which is just pip install, I'm going to say tick tokenizer. Tick token, sorry, my bad. And tick token is a library from OpenAI that helps you to interact with different encoding models and stuff like that. So if you are working with an LLM and you want to send a huge amount of text, you don't know if that text can overflow the context window, you can use the tick tokenizer to compute the amount of tokens so that you don't overflow the context window when making an API call, something like that, right? So we're going to use it now to visualize how the BPE works. So we're going to say from tick tokenize from tick token dot underscore educational, you're going to go ahead and import everything from in there. I'm going to say encoding encode is going to be equals to the simple. I got this code from the official documentation as well. So simple byte pair encoding dot from tick token. You're going to go ahead and pass in which model we want. So we're going to use a CL 1000 kbase, perfect, and you're going to go ahead and pass in our word. So we're going to, instead of using that, I'm going to go ahead and simply pass in the initial sentence we have, which is low, lower, lowest, and then I can say lowering, which is some new words, so you can see how it handles some new words. We're going to use 840, 870, and then a full stop. So let's run this and let's see how it's going to visualize how this works. So it's going to start with the first word, which is low. So you can see split it up into individual characters L. So you can see each character has a space, different coloration right here. L has its own color, O has its own color, W has its own color. So you can see it merges L and O and W. So that merge forms into one token, and then merges L with LOW. So it forms the word lower. So you can see how it goes on ahead, and you can visualize how all this works. So you can see it goes ahead, and then this stands as a standalone space, as one space. Start from here, combine them, and then finally get 840, and then goes all the way and does that. Right, so that's basically how this tokenizer, this byte pair tokenization, byte pair encoding basically works. To visualize how we can use a BPE method in GPT-4 and see in a visual way how this whole process, which I've explained up here, comes together in here. Right, perfect. Okay, so now let's go ahead and look at the token behavior. So token behavior can be affected by a couple of things that I think you should know. The first one is the tokenization method that you use So we talked about the BPE, which is a byte pair encoding tokenization method. So it affects how your tokenizer behaves once it's done trading. We also have word-based, whether using word-based tokenization or character-based tokenization, that will affect the final behavior of your tokenizer. Also, we have the initialization parameters such as the vocabulary size, the spatial tokens such as end of sentence token or other masking tokens, CLS tokens, unknown tokens, paddings, and other stuff like that. All those come together to affect the final behavior, how the model handles capitalization. Can the model differentiate between a capitalized and a non-capitalized word? All those affect the final behavior of your tokenization model. Also the domain in which the data was trained on. So if you want to work with a model, maybe financial LLM, then it's best if you develop a tokenizer that's just for financial data. In this case, we don't have this kind of very domain specific tokenizers and LLM models at the moment, because it's very costly to build your own tokenizer. You have to have a ton of data, GPUs, and do a ton of training, which most organizations don't have access to. But if you have the money and you're doing something very specific to maybe to a given language or a given domain, then you want to train your own tokenizer and then use that tokenizer to train an LLM, then that can really affect the way it behaves. Okay, so moving on to some things I think you should know. So after a tokenization is initialized and trained on vast amount of data, it is used to train an associate language model, right? This creates a permanent link between the tokenizer itself and the language model. In the sense that you cannot use a language model with a tokenizer it was not trained upon. Like we look at a GPT-4 tokenizer, it can only work with GPT-4 language model, right? So each language model has its own tokenizer that it works with. So if you train a language on tokenizer, a language model on tokenizer A, then you can swap it up with tokenizer B. It wouldn't work. So that's something I think you should keep in mind. Yeah, so that brings us to the end of this video, and I hope you found this helpful and you have learned a lot from these different tokenization methods, and this video was of value to you. So guys, thank you so much for watching, and I hope you found this helpful. Again, you can always contact me if you want to reach out to me. You can reach out to me on Medium, where I have an article of this as well. So I have a written article of this video as well. You can follow me on YouTube. Hopefully, you're watching this video at Coded Prince. You can follow me on X at Prince_Cramper, or you can get to me on LinkedIn. I'm much faster to respond to you on LinkedIn if you want us to connect in there and share some ideas and brainstorm, or you have any things that you want to us to work on together. You can reach to me at Prince Cramper on LinkedIn. So guys, that's all for this video. Thank you so much for watching, and I hope you found value out of this. So see you in the next video, where we'll be going over embeddings, and how tokenization come into the picture as well. Thank you guys so much, and see you in the next video. Keep safe.